Hello everyone, I'm HighSchoolPhysicist. Welcome back to my channel. My motivation in creating this channel is to talk about some topics in physics for audience at high school level or above. This channel emphasizes in mathematical tricks that are used by physicists that may be appreciated and learned by young students, and finally can attract young generations to love physics. Today I'm going to be talking a topic called internal symmetry. Symmetry is object transformations in mathematics that leave that object unchanged. Some examples with regard to space are translation, reflection, and rotation. In physics, internal symmetry is symmetry that has nothing to do with space. Curious to know? We shall see shortly. Before starting, let me mention the maths needed to follow my story in this video. The first is function, the second is matrix which includes multiplication, inverse, and determinant. The third is trigonometric functions which include sinus, cosinus, hyperbolic sinus, and hyperbolic cosinus. And the last is complex number. There is no calculus needed. Apologize me that there is going to be intensive maths. I promise there are some homeworks and challenges for the audience, but it's fun, like I had fun in preparing this video. Let me explain by providing you an example. Let us see a function L with two variables a and b. We'd like to transform variables a and b into other variables named a1 and b1 with the following formulas, with theta as a continuous parameter. Some people like me like to use matrix notation, and we name the matrix in the middle is transformation matrix M. We can see some degree of symmetry in matrix M. We also change L into matrix notation. Then what happens to A1 and B1? Here is the calculation of A1 and B1 using transformation matrix M. Superscript T means transpose of the matrix. Then concisely we can write, let us continue the calculation. MTM becomes identity matrix, so we see the same form of L on the left and on the right. Thus, transforming variables using matrix M does not change the form of L. So it is said that L enjoys internal symmetry that has nothing to do with space. Now we arrive at homework like I promised. We see original M is almost symmetric, differs only by a negative sign. You might ask, like me, will it work if M is, as the new matrix is more symmetrical than the previous one? The second question is, can we use hyperbolic trigonometric functions like hyperbolic sinus and or hyperbolic cosinus? Try to do it yourself, then see the answers that I provide at the end of this video. I'll give you two challenges. The first challenge is I modified L into L1 by removing the power of 2 in variable a. Please pause the video now and think by yourself first. Welcome back. This is the hint. Pause the video again. Okay, the key is change variable. Let a2 equals to square root of a. With this variable change, we can bring L1 into the same form as L, and we can solve with the same transformation matrix M. Is it easy for you? Now the second challenge. I modified L into L2 by changing the addition into subtraction. Please pause the video now and think by yourself first. Welcome back again. This is the hint. Pause the video again. Okay, the key is change variable. Let b2 equals b times imaginary number I. Again, with this variable, we can bring L2 into the same form as L, and we can solve with the same transformation matrix M. Is this also easy for you? Seeing this problem, my natural instinct tickled me. I converted L2 into matrix notation, and we'll see what is going to happen. This is the fun part. First form is like this, and the second form is like this. These two forms are almost symmetric, differ only by negative sign. Now take a look at this form. According to me, this form looks better than the previous two forms. Then I saw 1, -1 matrix as a hint. Unfortunately, this is rather advanced trick, but stay with me. Determinant of 1, -1 matrix is -1. I think making matrices with determinant 1 will help. So let's try this 3 by 3 matrix or 4 by 4 matrix which have determinant of 1. At this stage, I choose 4 by 4 matrix because it looks more symmetrical to me. To transform 2 by 2 matrix into 4 by 4 matrix, we have to transform A and B into two component number. So A is split into A1 and A2, and so is B. Now we try to find the transformation matrix M. After searching for a while, this was the first matrix that I found. The element of this matrix remind me of Pauli matrices. The strategy also reminds me of the strategy that used by Paul Dirac to formulate Dirac equations. The variable splitting means there is particle and antiparticle pair. Dirac has just predicted the existence of positron. So we have found the internal symmetry for the function L2. Now it's time to discuss the homework. Does this symmetrical matrix M work? Unfortunately not. For question 2, we replaced sinus with hyperbolic sinus and cosinus with hyperbolic cosinus, but we had to include a factor of 1 over square root of hyperbolic cosinus of 2 theta. You may verify this. In conclusion, we have learned about internal symmetry, which is the symmetry that has nothing to do with space. We gave an illustration starting with the function L with variables a and b. We transform a, b into a1, b1 with transformation matrix of M. This gives the new function L with variable a1 and b1 having the same form as the original function L, a, b. Secondly, we work out some two similar functions. In this occasion, I want to thank my fellow dark calligraph who assisted me in web technical and also marketing matters, considering subscribing to his channel. See you next time and thanks for watching.